Secondary cells are galvanic cells that must be recharged before they can be used. They also can be recharged many times. In the charging process, the spontaneous feasible reaction that produces electrical energy is reversed. In other words, the charging process needs outside source EMF to occur. Here is a simple animation shows a typical secondary cell. During the discharging process, the electrons flow from the anode to the cathode, where the anode is the negative electrode and the cathode is the positive electrode. On the other hand, in the charging process, we use a battery as the electrical energy supply, so the non-spontaneous reaction can occur, and the products can be converted into the reactants again. So we have some examples on secondary cells. Our first example is about the nickel-cadmium battery. The active components of a rechargeable nickel-cadmium battery are nickel hydroxide at the cathode and cadmium at the anode. For the electrolyte, usually potassium hydroxide is used. Due to their low internal resistance and very good current conducting properties, nickel-cadmium cell can supply extremely high currents and can be recharged rapidly. At the anode, cadmium loses 2 electrons and combine with hydroxide ions to form cadmium hydroxide plus 2 electrons. At the cathode, hydrated nickel oxide is reduced and reacts with water to form nickel hydroxide and hydroxide ions. We are moving into our second example, which is lead storage battery. The battery is composed of 6 cells in series to give an overall 12 volts supply. In the discharged state, both the positive and the negative plates become lead-2 sulfate. The electrolyte loses much of its dissolved sulfuric acid and becomes primarily water. So the reactions of the cell are as follows. At the anode, lead loses 2 electrons and reacts with hydrogen sulfate to give lead sulfate and 2 electrons. At the cathode, lead-4 oxide gains 2 electrons and reacts with hydrogen sulfate to give lead sulfate and water. Combining these 2 reactions, so we get the overall reaction as follows. So let's move on to the charge chemistry of the battery. In the charged state, we use an outside source EMF so the non-spontaneous reaction can proceed. Unlike the discharging process, the anode and the cathode signs will be reversed, so the anode will have a plus sign and the cathode will have a negative sign. At the cathode, electrons are being pushed into the cathode from the EMF source. The cathode here has negative sign. Lead sulfate gains 2 electrons and is reduced into lead again. At the anode, electrons are being pulled out of the anode by the EMF source. The anode here has a positive sign. Here lead sulfate loses 2 electrons and reacts with water to give lead-4 oxide. In the end, don't get confused. The anode is the electrode at which oxidation reaction occurs, and the cathode is the electrode at which reduction reaction happens. That's a general rule.
Nickel metal hydride battery is a secondary battery or a rechargeable battery where the reactions are reversible. Let us discuss the construction and working of nickel metal hydride battery. The anode used in nickel metal hydride battery is metal hydride. The cathodic active species is nickel oxyhydroxide and the electrolyte used is potassium hydroxide. It can also be represented as diagrammatic representation of nickel metal hydride battery is as follows. Nickel metal hydride battery anode and cathode both are made up of nickel foils. The anodic active species is made up of metal hydride, where the metal hydride is an alloy of either zinc, vanadium, titanium, chromium, etc. The cathodic active species is made up of nickel oxyhydroxide. Both are separated by a insulator or separator which is made up of polypropylene. This entire nickel metal hydride battery is kept in a glass or a steel container. The electrolyte used here is potassium hydroxide. So let us discuss the cell reactions. The cell reactions, as we discussed earlier, are reversible reactions. The reactions occurring at anode are the metal hydride here undergoes oxidation in presence of electrolyte to give the metal respective metal and water and electrons. These electrons liberated at anode are used up in the cathodic reactions. Since the nickel oxyhydroxide is the active species at cathode, this undergoes reduction in presence of water and electrons to give nickel hydroxide and 4 hydroxyl ions. The overall reaction is as follows: metal hydroxide, hydroxyl ions, nickel oxyhydroxide gives metal, nickel hydroxide and 2 hydroxyl ions. Why are we getting here 2 hydroxyl ions here? Because in anodic reaction 2 hydroxyl ions are used up, whereas in cathodic reaction 4 hydroxyl ions are liberated. Therefore 4 minus 2 is 2. Some of the applications of nickel metal hydride battery are as follows. The nickel metal hydride battery is used in electronic devices such as computers. So before lithium ion batteries came into existence, these were the batteries which are used in computers, and these are the batteries which are used in the electrical vehicle.
Battery works. Smartphones, laptops, and Teslas all get their power from rechargeable lithium-ion batteries. All batteries have the same basic 3 parts: a positive electrode called a cathode, a negative electrode called an anode, and a chemical layer called an electrolyte that lets electrical charges flow between the electrodes. In lithium-ion batteries, the electrode combo is usually a lithium cobalt oxide cathode and a graphite anode. When you plug in your phone, electrons enter your phone's battery and cause lithium ions to meet up with them at the anode. Once at the anode, the lithium atoms nestle in sites between the graphite's carbon layers. When you unplug your phone, though, the process reverses. Lithium atoms at the anode start losing their electrons. The electrons zip through the circuit, providing the current to run your phone. Meanwhile, lithium ions journey through the electrolyte. They reunite with the electrons at the cathode. These processes keep going until all ions reach the cathode, causing that dreaded flashing battery symbol. Every time you burn through 100% of the battery's charge, which is called capacity, you take the battery through one charge cycle. Each cycle inches the battery closer to death by shaving off some of its total capacity. So, here's how to keep your phone's battery charge and life lasting longer with science. Heat does nasty things to lithium-ion batteries, and we're not talking thermonuclear level heat here. We're talking about when you forgot your phone in a hot car or left it in the sun at the beach. As your phone battery gets warm, the heat speeds up the chemical reactions that cause the battery to go kaput. These reactions break down the electrolyte and form products on the anode. This blocks lithium ions from nestling into the graphite. Fewer sites means less capacity, and you'll have to charge your phone more often. Even worse, heat can start a thermal runaway. Once the cobalt oxide gets hot enough, it starts a cycle of reactions that throw out more and more heat. All of this heat starts to boil the liquids in your phone's battery, building pressure until the battery explodes. Lithium-ion batteries don't need to be fully discharged before recharging, unlike nickel batteries. Nickel batteries suffer from the memory effect, meaning that unless they're at 0%, they'll forget part of the capacity when recharged. But lithium ions never forget, and they loathe a full discharge.
So next is lithium polymer batteries. So here the anode used would be lithium metal oxide and cathode is graphite. Electrolyte is ethylene carbonate. So as you can see here, lithium ions, that is positively charged lithium ions, flow from the anode to cathode and thereby electric current is produced. So while we are recharging the battery, the same process is reversed. That is, the ions travel from the graphite to the anode, which is lithium metal oxide.